Good morning again, Year 12. So today we are going to be looking at organohalogen molecules. So that is molecules similarly to the ones we looked at last time. However, to start you off, I would like you to have a go at the question that is on the screen currently, which is all about bond enthalpies, which of course we did right at the very start of Year 12. And is a little bit of a throwback. So I will pause here to let you do that. Okay, so hopefully you paused and you have completed it. So the mark scheme for this, because this is one of the current specification questions, says that the standard enthalpy term enthalpy change of formation is the enthalpy change when 1 mole of a compound, first mark, is formed from its elements, second mark, and then our standard conditions are 25 degrees C and 1 atmosphere, or any of the others. Okay, it can be when 1 mole of substance or 1 mole of product, as you see on the purple bit. For our next one, for the enthalpy change of formation of our ammonium chlorate, well, it is that equation there. Do you remember that because it's an enthalpy change of formation, we needing to be producing 1 molecule of that ammonium chlorate from its elements under their standard conditions? So you'd get 1 mark for the correct species and 1 mark for having your state symbols and it balanced. Okay. The last question, I need a little bit more space, so I have it on here. So the first thing that I would do is I'm going to construct myself a Hess's cycle. So I will start off with the equation that we were originally given, and we will refer back to the enthalpy change of that. If we have a look at the table for a moment, then we will hopefully notice that it's enthalpy changes of formation, so delta HF. That is of course why they got you on this question to tell you what is the enthalpy change of formation for ammonium chlorate. So they're trying to prep you. So that means that once I've got that equation, I know that my Hess's cycle, I'm going to start with the elements down at the bottom, because I've been told enthalpy changes of formation, I'm making these substances from their elements. That must mean that my reaction arrows are going to go from my elements down at the bottom to my reactants of the original equation and also to the product of it. Okay, I know that lots of you find it a little bit of a struggle to deal with that, but remember that in this question they got you just here, maybe not on red, let's go for blue, they got you literally here to give one of those reactions. Okay, and note that of course we're going from the elements to the compound. So that's why we're going from the elements down at the bottom to the compounds and our reactants and products. Now, it is a slightly tricksy one, in as much as we're wanting the enthalpy change of formation of NO rather than just the enthalpy change of the reaction, and that of course means that we're working out what something is going from here to here, which does make our life a little bit more awkward. Let's just get rid of that line and find clear pen markings. So, we first work out how many lots of the enthalpy change on our reactant side we're doing. We're doing 3 lots of the enthalpy change of the formation of ammonium chlorate, so that's 3 lots of minus 295, because that's what they told us it was in the table previously. And the sum of all of those enthalpy changes is minus 885. The reason that we don't have to worry about aluminium is, well, it's an element and it's in its standard state. So we'd be going from aluminium metal to aluminium metal, and there is no enthalpy change with that because we've not done anything. Okay. On the product side, we would go, okay, we've got 1 lot of the aluminium oxide being produced, 1 lot of the aluminium chloride being produced, 6 lots of water, and 3 lots of nitrogen oxide. So we would do the appropriate numbers of each enthalpy change. Do note, and I haven't put the units for all of these, no, I haven't put the units for all of these, but all of these are in kilojoules per mole. Okay, I just haven't written that. Okay, if we do that sum, and let's clear all the pen markings, we have that all of those enthalpies added together are minus 3,832 and 3 lots of whatever the nitrogen oxide's enthalpy change is. Okay. We were, of course, told that the reaction at the top had an enthalpy change of minus 2,677. Okay. Now, there are a number of ways of doing this next step, but I like my arrows, so I'm going to say that this route, my route A, is the same as this route, so we could call this B and this C. So that means that A equals B plus C. Okay. If we substitute in all of our information that we have, well, that means that minus 3,832, I have 6 nitrogen oxides being made there instead of the 3 that it's supposed to be. I apologise. Let's just correct that to 3. Equals minus 885, and we could imagine that we had a plus there because we're going in the same direction as this arrow, so we're adding that enthalpy change. Again here, we're going in the same direction as that, so we're going to add that enthalpy change. And I always lay it out like this because I just want to be thinking of, am I adding or subtracting it? And I don't care whether it's a positive or negative number yet, and I will just whack it into my calculator as is, as you can see it on the screen, with those brackets in. Okay, so if we do a quick little bit of maths, and again, I thought I had changed that, so that should be 3 as well. We have that we've now got minus 3,832 plus 3 lots of nitrogen oxides. Enthalpy change is equal to minus 3,562 kilojoules per mole. If we move the minus 3,832 to the other side, we'll take away a negative number, so we're adding it. So we have an equation that looks like that. If we do that sum, that gives us that 3 lots of the enthalpy change of nitrogen oxide gives us an enthalpy change of plus 270. So to work out what 1 is, we would divide it by 3, and that gives us an enthalpy change of 90 or plus 90. Now, the important part as far as the mark scheme is concerned is effectively calculating this correctly, these two correctly, and then basically doing this sum to here, and then finally that sum to there. If, of course, you get that final answer, you get all 3 marks. Okay? So, I said we were going to have a look at organohalogen compounds and the environment. This is, in fact, the last part of the Year 12 course that we need to do. So, hopefully, if you have a look at what the specification says on the screen, it's not actually that much. It's a lot less than we went through last time, so this hopefully will be a slightly shorter video. So, what are they? They are, well, organic molecules that contain at least one carbon-halogen bond. Typically, we're looking at chlorines or fluorines, but not exclusively. So, for example, this first one is a solvent. It's chloroform or trichloromethane. If you go on to university, you'll probably use that quite a lot. It doesn't work like they show you in the films of putting it on a rag and immediately people fall unconscious. You have to be exposed to it for some time. Similarly, we've used it as flame retardants, so you probably know, or you might not know, that most furniture and stuff should have some flame retardants built into it so that it doesn't burn very easily. And most importantly, they were used as refrigerants. So we have a couple of examples there. So we have difluoromethane, we have difluorochloromethane, and we've got dichlorofluoromethane. But those last ones are particularly our chlorofluorocarbons, our CFCs, because they contain chlorine and fluorine. And those are the ones that we're most interested in today. The reason that we are interested is because of their interaction with the ozone layer. Okay, so the ozone layer is a layer in the atmosphere, and it is made of ozone, which has the formula O3. So it's a slightly different looking molecule than oxygen, but it is formed from elemental oxygen. And the way that it is formed is because when we get up to that layer, there's a good concentration, effectively, of ultraviolet radiation, and that causes some oxygen molecules to be broken down by homolytic fission, producing oxygen radicals. Those oxygen radicals can then interact with the oxygen molecules that are still in that environment, and then they are forming ozone, O3. But at the same time, ozone is really important because the ozone layer absorbs most of the UVB, in particular radiation, which is the damaging form of UV radiation. It does that by absorbing it into the bonds and causing those bonds to break. So not only is it formed because of UV, but it is being broken down as well. And we get our ozone molecule decomposing into oxygen and an oxygen atom radical. That oxygen atom radical can then, of course, go and react with some oxygen and reform ozone. So ozone is a steady state within the atmosphere. It's being broken down and formed at the same rate, so it is in equilibrium. We can therefore represent it using this reversible reaction. Okay. CFCs cause a problem though. Okay, because they are absolutely amazing at ground level. They are inert, so they don't react. They can be used as fire suppressants, and they were used as propellants in aerosols. And of course they're gases, so they can be used as refrigerants because you want to be able to cycle through a state change. That gets you really good cooling or potentially heating issues. The thing is that they are problematic at a higher altitude because they've got those carbon halogen bonds. Those can be broken down by UV. And now the guy that actually invented CFCs is a guy called Thomas Midgley, and he was a great chemist but a really unfortunate chemist because he managed to produce two really crucial compounds for the 20th century. CFCs, which allowed refrigerators and things to come along and be accessible by lots of people, but with the associated problems that we're talking about. And he's actually the guy that came up with the idea of using a lead-containing molecule compound to prevent a condition called knocking in car engines. And it turns out that using leaded petrol was probably not great, and it's a pretty toxic compound. So he unfortunately had two great discoveries which were really amazing at the time, but have actually been pretty terrible for the planet overall. What you don't know, hey? So, the ozone layer depletion. That's ultimately what we're interested in today. So, what first happens is our UV light comes along, and it will cause some homolytic fission to occur. It will preferentially happen to whichever is the weaker bond. So in our dichloro-difluoromethane, it's going to be one of the carbon-chlorine bonds. So we're going to create our two radicals that we see here. We're most interested in the chlorine radical over here. No, I don't want to stop. Because now we've effectively done an initiation step, like when we talked about radical substitution all those months ago. That chlorine radical can take part in a propagation step. And that chlorine radical can attack a chlorine radical can attack an ozone molecule, making our ClO intermediate, which is a radical, and a molecule of oxygen. It can then, because of course by the normal breakdown of ozone we have some quantity of oxygen atoms around in the environment, that radical, that ClO radical, can react with an oxygen atom, an individual oxygen atom, creating our chlorine radical again, and an oxygen molecule. That gives us an overall reaction, and I just need to write it here, is if we do it the way that I always do, of putting all of the things on the reactant side together, so we've got a Cl radical, and an ozone, and a ClO radical, and an oxygen atom, and we've got that reacting to form a ClO radical and an oxygen molecule and a chlorine radical and O2. We want to now get rid of things that appear on both sides. No. So we will see that chlorine radicals appear on both sides, so we'll get rid of those. Our ClO appears on both sides, so we'll get rid of that. So we are left with our overall equation is ozone plus an oxygen atom creating 2 molecules of oxygen. And that's a problem, because we now have removed, not permanently, but we have removed from that dynamic equilibrium a substantial quantity of ozone. Now, there is an alternative way that we can draw these 2 propagation steps, which I'll show you on the next slide, but this is a problem. This was why, back in 1987, the Montreal Protocol was signed, effectively trying to get the country, well, the world, to stop using CFCs, because we were damaging the ozone layer. You may well have heard of the hole in the ozone layer above Australia. That gradually, over the last, 30-something years now that we have stopped using these ozone layer depleting chemicals, mostly, is returning back to its equilibrium that it was at before. But it is taking a substantial amount of time, considering how little time it took for us to damage it. Now, in those propagation steps, we could alternatively have a chlorine radical reacting with ozone to make our ClO radical and a molecule of oxygen. And we're also allowed to show our chlorine, our ClO radical reacting with another molecule of ozone to create our chlorine radical again, and here 2 molecules of oxygen. That will give us a slightly different overall equation, in as much as if we just get rid of the things on here. We've got chlorine radical, we've got ClO radical, so that gives us an overall equation of 2 lots of ozone reacting to form 3 lots of O2. Do note here, especially importantly, that it is not a reversible reaction. That's why this is fundamentally so problematic. Okay, but of course, is it just CFCs? Well, no, it's not. One of the other major radicals, and it could be any radical that is present in the ozone layer, but it's relatively difficult to put things there, but one of the ones that we do find is the nitrogen oxide radical. So you might remember that nitrogen oxides were made when we have a large amount of heat and pressure, like in engines. So we actually find that we generate this in aeroplane engines, because we've got nitrogen and oxygen providing a lot of heat and pressure, and in fact from lightning strikes, but that's a natural course. That's not really a worry for us. We can't really control that. So fundamentally it's the same. We have our nitrogen oxide radical. It reacts with an ozone molecule, creating our nitrogen dioxide radical and oxygen molecule, and then that nitrogen dioxide radical reacts with an atom of oxygen to reform the radical that we had at the very start, and forming some oxygen. And if we just cancel it out directly on here, I don't want that one, let's go for that. We have our radicals cancelling out. We then have our other radicals cancelling out, giving us once more ozone plus O going to 2 lots of O2. And just like in this previous example, if I go back to here, where we could have our second propagation step reacting with a molecule of ozone instead of reacting with an oxygen atom, we could have exactly the same here, and we would just end up with exactly the same overall equation where we've got 2 molecules of ozone decomposing to create 3 molecules of oxygen. So that is it. That is the Year 12 course for us. We will have a little look back at some bits, but after Easter we are going to start looking at some of the Year 13 content. So have a good Easter. I know Miss Forbes is going to provide you some PLCs, but have a good little bit of a rest, obviously in these slightly strange times, but rest up and come prepared for learning about, with me, some rates stuff, but a little bit harder than what we did at the start.